Hey everyone, and welcome back to blackboardAI. Today, we are diving deep into a fascinating graph problem from Codeforces Round 1029, Division 3, Problem G. Omg Graph. This one truly stretches our understanding of pathfinding, moving beyond simple shortest paths. If you love graph theory and clever algorithm adaptations, you are in for a treat. Let us break down the problem statement. We are given an undirected, connected, weighted graph. Our goal is to find a path from vertex 1 to vertex n that has the minimum cost. But here is the twist. The cost function is not the sum of edge weights, like in standard Dijkstra. The cost of a path with edges w1, w2, wk is defined as the minimum edge weight on the path plus the maximum edge weight on the path. So min wi plus max wi. And importantly, the path does not have to be simple. You can revisit nodes and edges. Our challenge is to find the path from 1 to n with the absolute minimum of this unique cost. Now, if your first thought was Dijkstra, you are on the right track, but it is not a direct application. Standard Dijkstra minimizes the sum of edge weights. Here, our cost depends on both the smallest and largest edge. This dependency makes a direct greedy approach difficult. Because adding an edge might increase the max, but decrease the min or vice versa in non-additive ways, it is not a simple path sum. So how do we tackle this unusual cost function? The brilliant insight, as hinted, is to apply a clever strategy. Try fixing the minimum edge on the path. The core idea is this. What if we knew which edge was the minimum weight edge on our optimal path? Let us say this edge is EJ with weight WJ. If we fix WJ as the minimum edge, then the cost becomes WJ plus the maximum edge weight across all edges on that path. So, WJ plus max k WK. The key here is that if we iterate through every single edge in the graph, pretend asterisk that specific edge is the minimum weight edge of the optimal path, calculate the best possible cost under that assumption, and then take the overall minimum of all these calculated costs, we will find our true answer. Why? Because the optimal path asterisk must asterisk have some minimum weight edge, and our process will consider that specific edge at some point. This reframe simplifies things immensely. Instead of trying to find min wi and max wi simultaneously, we fix min wi to be wj for a specific edge j. Then, we only need to minimize max wi for paths that include wj. A path that includes edge uj, vj with weight wj can be visualized as a path from 1 to uj, then the edge uj, vj itself, then a path from v, j to n asterisk. The total maximum edge weight on this combined path will be the maximum of the maximum weight on the path from 1 to u, j, the maximum weight on the path from v, j to n asterisk, and the weight wj itself. Because w, j is part of the path, it could be the maximum weight on the entire path. This brings us to the crucial part. How do we find the minimum possible asterisk maximum asterisk edge weight on a path from one node to another? This is where a clever adaptation of Dijkstra comes in, sometimes called max Dijkstra or Min+Max path. Recall standard Dijkstra. It greedily explores nodes, always picking the one with the smallest asterisk sum of weights found so far. The key insight is that when a node is extracted from the priority queue, its dist value is finalized as the minimum sum. This same logic holds if we change the sum to maximum. Here is how max Dijkstra works. 1. Initialization. Set dist of source to 0 or a very small number like the minimum possible edge weight, depending on context, and all other dist values to infinity. 2. Priority queue. Use a min priority queue, storing current max weight on path node. 3. Relaxation. When we extract max weight u from the PQ, for each neighbor v of u with edge weight w. Calculate new max weight v equals max of max weight u. W if new max weight v is less than dist of v, update dist of v and push new max weight v to the priority queue. After max Dijkstra finishes, dist of x will contain the minimum possible maximum edge weight on any path from the source to x. Now, let us assemble our full solution. 1. Run max Dijkstra from node 1. This will give us max dist from 1 for every node u, representing the minimum possible maximum edge weight on a path from 1 to u. 2. Run max Dijkstra from node asterisk n asterisk. Yes, from n asterisk. Because our graph is undirected, a path from v to n asterisk is the same as a path from n asterisk to v in terms of maximum edge weight. So, we run max Dijkstra from node asterisk n asterisk to get max dist from n asterisk for every node v. This tells us the minimum possible maximum edge weight on a path from v to n asterisk. Now we have all the pieces. 3. Iterate over all edges. Initialize min overall cost to a very large number. For every edge uj, vj with weight wj in our graph, calculate the candidate maximum edge weight for paths containing this specific edge uj, vj. Current path max weight equals max of max dist from 1 for u, j, max dist from n asterisk for vj, wj. This captures the bottleneck of the path from 1 to u, j, from vj to n asterisk, or the connecting edge wj itself. The total cost for this specific edge wj, being the minimum, is wj plus current path max weight. Update min overall cost equals min of min overall cost, wj plus current path max weight. Finally, our answer is the min overall cost found across all these calculations. This method guarantees we have considered every possible minimum edge for the optimal path and found the best overall maximum for each case. Let us talk complexity. We run max Dijkstra twice. Dijkstra with a priority queue typically runs in O of m log n, since m can be up to 2 times 10 to the power of 5, and n up to 2 times 10 to the power of 5, O of m log n is efficient enough. Then, we iterate through all m edges once to calculate the final minimum cost. This is O of m, so the total time complexity per test case is dominated by the 2 Dijkstra runs, O of m log n. Given the constraints, sum of n and m over all test cases up to 2 times 10 to the power of 5, this O of m log n solution will pass comfortably within the time limits. To recap the ingenious solution. One, the problem, find path 1 to n with minimum of min edge plus max edge cost. 2. The trick, iterate through each edge wj, assuming it is the minimum edge on the optimal path. 3. The tool, adapt Dijkstra to find paths that minimize the maximum edge weight, max Dijkstra. 4. The solution, run max Dijkstra from node 1 for max dist from 1 and from node asterisk n asterisk for max dist from n asterisk. Then, for each edge uj, vj with weight wj, calculate wj plus max of max dist from 1 for u, j, max dist from n asterisk for vj, wj. The minimum of these values is our answer. This problem is a fantastic example of how seemingly small changes to problem definitions can require significant shifts in algorithmic thinking. The max Dijkstra is a powerful technique to have in your toolbox. If you found this explanation helpful, please hit that like button, subscribe to BlackboardAI for more deep dives into competitive programming problems, and let us know in the comments if you have any questions or alternative approaches. Thanks for watching and happy coding!